solve?
It's like using Euler's method, but taking like you basically make multiple of them and take averages amongst each one of those like slope values, so you can kind of get an average slope.
It's numerical approximation of different equations. That's all it is. There are several different methods, and they each have pluses and minuses.
Like either how computational heavy they are, or how much stress they put on CPUs versus their accuracy. That's kind of the trade-off. Like the more accurate they are, the more computational heavy. So either you have a bunch of people just grinding, or your computer's like bogged down because they have so many intervals to calculate.
All right, as for today, so we spent 3 days on setup of doing the transformation for Laplace and then the inverse transformation. Finally, we're going to do that all in one step. All right, so we're finally going to see actually how to use Laplace transforms and some real benefits that it contains within. There's a lot of algebra and everything, but what we've seen so far is, you know what Laplace transform doesn't have a lot of? It's actual calculus. All right, it's boiling all this down to an algebra problem. What we are going to use, all right, is the definition of differentials with the transform. This is now number 35, 36, and 37. And I said from the beginning that those were super important transforms. All right. This is like 35 and 36. This guy is 37. Right. It basically, notice what it's doing. Laplace transform of a differential turns it into, functions with conditions, and everything is subtraction. Notice in the generalized form, when we get to higher order, we're going to use this one. For now, we're just going to use these two, because we're just dealing with first and second derivative. Oh, it says right there, 35, 36, 37. The biggest thing, is we're going to do some homogeneous and non-homogeneous equations, and we're going to see ones that could be solved easier other ways, we're going to solve them with Laplace transforms, then we're going to see some that only can be solved with Laplace transforms. Also, we have a note, I have a note later. All our initial conditions are at t equals 0 because of what the equation actually has, and we're going to see a method, notice the initial conditions is 0. We're going to see a method of how to adjust that as well. All right, so let's look at an example. So finally, we're going to solve the IVP, with Laplace transforms. Now notice this one, non-homogeneous. We could use that method that you both love to solve this instead. What method did we use to solve this?
Method of coefficients.
Undetermined coefficients, the one you guys both struggled with. Okay, so this should be your alternative. Okay.
When in doubt.
So we're going to take the Laplace transform of the whole thing.
May I ask a quick question?
Yes.
Is there ever a time that you have to use the undetermined coefficients, or you have to use Laplace, or are they both seriously interchangeable?
They are, we're going to see in the next session, when there's only one approach. The time that you wouldn't want to use Laplace transforms is if the partial fractions are something you just can't solve it. You can't break it apart sometimes. But most of the time, are they interchangeable? Yeah.
Okay.
But we even saw the variation of parameters, We saw when there was times where those weren't interchangeable. You had to use variation of parameters. Certain times, is it possible that I have a function here that I can't do a Laplace transform of? Notice in our sheet, there are some functions in there that we don't have transforms for. Is there any that jump out that you don't have a transform for?
Tangent.
The other half of the trigonometric functions, We have sine and cosine, which is like a vast majority, which is the same thing we talked about with undetermined coefficients. Notice, I don't see tangent, secant, cotangent. That's problematic, And so that's basically the idea. Yeah, because this is not an exhaustive list, but pretty close. And I was like, I don't see an approach for those. That's the thing.
Okay.
So yes, Are they interchangeable? A lot of times, 100%. All the time, no.
Okay, sweet, thank you for that.
Okay, so, all right, using linearity, because this is basically the strength of Laplace transforms. So, all right, I have the Laplace transform of the various pieces. Now this, right, this right here, this is number 36, okay? This guy right here is number 35. Good news, the Laplace transform of y. I don't really see that one in the sheet.
Was that just one?
Not quite. That is actually go all the way up to above 1. The function f of s is the Laplace transform of a function f of t. That actually will just become
1/9?
huh?
1/9?
No, it's above, not number 1, above that.
Yeah.
The definition of the Laplace transform just is going to become y of s.
Okay.
Right? Big. Let's make this big y. Because this right here is basically y of t, right? That is a function. And I could just call this, let's call it freaking A's and y's. All right, y, I would more appropriately use that y. Because this is y of t, all right? Or f of t. And this becomes f of s, or big y of s, however you want to, whatever you want to call it. I was like, just because it's easier for me to write capital S than capital Y's. I was like, this is the definition of what a Laplace transform is. And then this guy over here, that's piece of cake, right? What is that guy?
T to the n.
1/s².
Yeah, you're absolutely correct. That's number 3.
Yeah.
Okay, so these guys. So what this is going to become, this becomes s² f of s minus s y to the 0 minus y prime of 0. Write that out. Put that in brackets. Minus 10. All right, that's number 35. S f of s minus, keeping out some y's, right? Just so we, because our initial conditions is y's. Plus 9 f of s equals 5 all over s². I could bring that through, but here's the strength of Laplace transform. Y of 0, y prime of 0, what are those?
Initial conditions?
Initial conditions. So here's the strength of Laplace transforms. We're going to input our initial conditions, right, into the function, all right, simplify it, and then transform it back. And when we get to the end, we're going to find our actual solution, right? The undetermined coefficients method. Every single method we saw in chapter 4 and chapter 3. At the end, what did we have to do? We have to take derivatives and find the initial conditions. This puts in the initial conditions, so at the end, we don't get a general solution. We get the actual solution as
In one swing.
yeah, in one swing throughout this process. So that's a real strength. And given, right, how much you guys love undetermined coefficients method, this means you get to avoid them. I was like, and so that's that again, there are ups and downs in Laplace transform. The algebra, it's gonna get rough. It's gonna be partial fractions. Are we gonna be able to do the cover-up method every single time? No, right? Which means that we have to grind through it. But you get to do so much all in this one step. All right, so f of s minus s times y to the 0 was.
Are we going to create a characteristic on this thing? Because it kind of looks like a quadratic.
You're absolutely correct. That's what I was saying. Because I could do this with undetermined coefficients, which means we would do the characteristic, and then I would take derivatives. Laplace transform skips all of that.
Okay.
That's the other method.
Okay,
I was like, this is a non-homogeneous second order function. The method we would approach this with is undetermined coefficients. Find the characteristic, find the general solution there, guess the particular function, put it all together, take derivatives, set them equal, find the values for the coefficients on the undetermined, then take derivatives, plug in the initial conditions, find then C1 and C2 from the general solution, and do all that. That's the method, right? That's how we solve this. That's exactly what we did in chapter 3 and chapter 4. Or we use Laplace transforms. So we skip all that with this.
cool.
Right? And I highly recommend, yeah, I was like, do it, but we just talked about how long that takes. And it takes a while, right? We saw how long it takes with the other methods. I was like, is this method faster? That's kind of a judgment call.
Okay,
I was like, but does it get all the way to the actual solution in one swing? Yeah.
okay.
And in my opinion, the worse the G of T function is over here, the longer Laplace takes. But also the longer the other methods take. Is there any super fast shortcut?
No.
No. It's like 6
Dealer-
or 1.
kind of
Kind of
dealer's choice.
what are you better at? Yeah, like what is faster for you?
Okay,
Me? I go Laplace transform every time.
it seems like this would be kind of the,
Because literally on the test, I said, don't solve for the coefficients because it takes freaking forever. I can do these faster than I can solve for all those coefficients in undetermined coefficients. But I mean, guessing a particular, I can do that way faster. It depends how far you're going.
that's fair.
Okay, what was it? -1. All right, minus y prime, which is 2. 10 minus 1. Okay, so our goal, all right, simplify that out once we plug the initial conditions in. Then remember, all right, remember what our goal is to get back to the initial function. I want this in terms of y, right? Y of t is our solution. So we just did a Laplace transform. Well, we have to go both ways. We have to do a Laplace transform and do an inverse Laplace transform. In order to do that, let's separate out, okay, and get this in terms of f of s. So basically, all we have to do is factor f of s out of this piece here. And then in order to solve for it, right, I'm going to send that stuff to the other side. And then, again, solving for f of s, divide. And so that's basically this process is what we do every single time. Now I can put this over 2 denominators or clean this up with a little bit of algebra. And this is going to become that denominator factors nicely. All right, bringing this down and common denominator among the other pieces. Because this now should look pretty familiar, right? The goal is get this into something and then do what technique?
Partial fraction.
Partial fractions, all right? Because basically, that's what we've been practicing with our inverse Laplace transform. So now notice, this is the stage, boom, got it all the way converted. This is in Laplace transform, right? The S space, all right? But we have to go back the other way. So we are doing the complete circle. And then good news, I get to do cover up, right? No, why not?
Squared.
Ah, I have an S squared there.
Ooh.
Okay. Multiply it through, you get some fun. And again, we should be getting pretty good at partial fractions. Solve it down. I was like, enjoyable partial fractions, no doubt. I was like, it is a nice grind. I was like, little matrix. It's that like you just sit there and grind the problem, and my brain almost turns off as I'm just like flowing through the numbers.
Transcendental state.
Yeah, I was like, because at that point it's just almost muscle memory. But then, all right, we got to turn our brain back on because f of s equals 50/81 over s plus 5 mass all over s squared plus. We do the partial fractions to get us to this form. All right. So once I have this, then what do? Why did I do partial fractions again? How did this help me?
To be able to retransform it.
Okay, so how do I transform it?
Evaluate each part individually.
Okay, all right, so what's the first part?
Over S.
Oh, this is just to our numbers. All right, so which one is this? All right, so to our table, this is
1.
we're doing the inverse Laplace transform. You're correct, it's not 1. I was just gonna write this first. We're doing the inverse Laplace transform of this whole thing. This guy is number 1. What about the next one?
Would that be 3?
That's 3. Number 3, and I guess we'll be specific with n equals
One.
One, yeah, that's our favorite one, right? That should be. I was like, and then the next one,
That'd be 2.
number 2, with A equals
9.
9. Remember, it is of the form negative, right? So if it's positive, good. Remembering that negative is annoying. And then lastly, number 2 with A equals
1.
1. Oh, that actually was pretty easy. I was like, those are not too bad at all. So the inverse Laplace transform, and now again, technically, which was y, which is why I should have put y of s, right? At this point, f of s, or f of t, y of t. Just say. And that actually all the way down to our function. Now, some of this should look kind of familiar, right? What does this guy over here look like? Back to our characteristic.
Oh, yeah.
That's the complementary solution right there. This guy over here, this is the particular, we just went different order because of how we wrote it, right? I was like, but this is the complementary, and C1, C2. Oh, look, the coefficients are already solved. The particular, same thing, right? We knew we had T, so we knew it was gonna be a T, A, T plus B. Oh, look, AT plus B. I was like, and we solved it. All right. Now, admittingly, I'm skipping the work and I'm going to skip the hefty work. The hefty work is multiplying this out and not screwing up. Right? Multiplying this out, then writing it all out, crossing out the terms and writing a matrix. I was like, but that's an algebra problem. We did literally 0 calculus in this problem. That whole thing boils down, okay, to an algebra problem. That is the strength of Laplace transforms. And algebra, like, that's what actually we use in the real world. When the calculus gets too difficult, computers do it. You need algebra to back yourself up. So I always think being the best at algebra is better than being fantastic at calculus, because the more difficult it gets, as you saw with numerical techniques, they do. All right, the computers will do that stuff. You need to logically verify your solutions. And so that's why this is the most realistic part as well. Okay, and then again, as I said, no general solution, and then initial conditions, getting constants, all in one stage. I was like, that is the strength, all right? These can get lengthy, but I was like, Laplace transforms, find the actual solution, all in one fell swoop. And again, see how it's going to get messy? Yeah.
Do Laplace transforms have any major limitations or any major conditions that they just don't work for?
It depends on what the
Tangent.
So we got
I
tangents.
was like, it depends on the non-homogeneous side of the solution.
Okay.
What? I guess I'll just spoil the fun here.
Spoil the fun.
I was like, the strength where Laplace transforms shine without a doubt is heaviside functions.
Okay.
There is no other, that's why they were initially
Created. Okay.
There is no other differential approach, numerical or otherwise, that actually can solve heaviside functions.
Okay.
Right? Looking at this, when you have a Laplace transform in this form, this is a heaviside function. You can't, piecewise functions, that's where everything else struggles and Laplace transforms shine.
Okay.
Can it be applied to other stuff? 100%. And that's why, right, they saved the best number for, all right, or the best equation, all right, for heaviside functions, because that's where they're actually the most useful.
Okay. Thank you for that. I was just kind of, it was like, if they're the same quote unquote as undetermined coefficients, why go through all this? But there's obviously a reason.
Yeah, and again, once again, here's another one. I can absolutely do this with undetermined coefficients method. All right, well, we're going to use Laplace transform because it kind of speeds up our process. All right, so Laplace transform of this whole guy. And that's the nice thing too. I mean, notice that I am doing the entire function within the Laplace transform. Also, you know what else Laplace transforms does? That remember with these, we were constantly getting this value, the coefficient in front of the y squared to be 1. Does that matter with Laplace transforms? Nope, because of linearity. It doesn't matter what that is, it just pulls out every time. So they don't have to be a beautiful form. It's actually our first differential equation that this is the form we needed. Nope.
No, no more.
All right, once again, I'm going to do S's because I like this so much. And then that guy is clearly just number 7. And then Laplace transforms, we plug in the initial conditions immediately, basically immediately after we get the transformation. Simplify it down, watch the negatives, that's just the biggest thing, negative, negative. That's also why I always start by writing it out, because these always have a bunch of negatives, and so watch that negative coming in, your signs flip, and all of a sudden your initial condition is, when you plug in the negative of your initial condition, your sign is negative, negative, negative. It was that one sign being off makes everything a mess from there on, because you're plugging those in so early. Solving this for f of s, though, of course. This does remind me though, you do want to judge, all right? So, because this is the actual process of the solve, right? I bring this piece over, then I divide by what's being multiplied by this, right? Standard algebra. When I look at this, so every time you want to take a moment and look at this, all right? Because is it worth combining this? I know I have to do partial fractions, but is it worth combining it? Does this factor?
Yeah.
It does.
6 plus 15.
I was like
No.
3 and 5, yeah.
Yeah.
I was like, oh, that was like, you had a moment where I was like, oh, I think it factors. No, this doesn't factor, which means that that's just as bad as this. So why do two partial fractions versus bring this over, right? Multiply this one by s squared plus 9 over s squared plus 9 and make it one piece.
Okay.
But every time you want to judge, because don't bring this over if you see a cover up right here, right? If I see a cover up, I'm like, oh, I don't want to bring it over because I have a cover up and then something bad. But if it's all bad, it's all bad. And here's also why it's bad. What does the partial fraction here become?
Like the actual like coefficients and stuff. Like, or
Yeah. Not the exact. I mean, what does it break into?
like S fourths and is that what you're asking? Like, what are you asking?
The A, B, C, A over, B over. Like, what does this become? This is factored. Remember, that doesn't factor. That doesn't factor. So it has to be what?
You have to like expand it out and then do each term individually.
Nope. Always want to get them done. They're in quadratics. It's as factored as it's going to get.
Is it like a over s squared, then b over a over 6s, c over 15? No.
One more time. Start again.
Is it a over s squared or a over s?
No. Okay. There's no. We can't be.
Or is it a over the entire left side and then b over the entire right?
Closer to one. Okay, hold on. We're back to where when I factored the other one out.
You pulled the S out in the last one.
Okay. This, right? This can all be broken down because these are single terms. But remember our rules of partial fraction. When we break this stuff apart, right? If you have squareds, remember you need a first degree in the numerator here. We're only able to break these apart, right? If it's first degree. If it's second degree, you need two terms and an S in the numerator. Remember, this is the one that causes us the most issue, okay? Because, we have to add zeros and stuff like that. So this becomes AS plus B, right? Over what?
S squared plus 9.
Yeah. It doesn't matter which one you do first, but just to keep with my numbers. Plus CS plus D all over the other one. So this is where the partial fractions get really rough, right? Because with all these S's in the numerator, the real love of partial fractions is when you don't have any S's in the numerator. Because when I start multiplying these out, right, when we go to solve this guy, I got to multiply by that denominator, and I'm going to end up with negative S cubed plus 2s squared minus 9s plus 24 equals, all right, AS plus B times S squared minus 6s plus 15 plus CS plus D times S squared plus 9, right? Now I have to FOIL both of those out. And that's not even the worst part yet. Oh, not even close. Just fine. So doing the partial fraction, okay? This is the easy part. Okay, we've got to set this up, break this apart, find the values. When we plug those back in, all right, this is what we end up with. Okay, so we did all that, and then get this. I'm not sure what I'm looking at. Because remember what we're doing. What are we trying to do?
Reverse transform.
Inverse Laplace transform. So to our table I go. Does anything look familiar?
Code, I guess between like 17 and 20.
Okay. Okay. Hold on. Which one are you looking at?
I must start on the left side.
Okay. Absolutely agree. Let's start here. This one looks a lot better. Okay. This is a plus.
So number 8.
Or
9 is negative.
what? Oh, no, other way. 7 and 8.
7. Oh, yeah.
7 and 8, right? That's basically 7 and 8. Okay, so that already looks like good news. So let's break that out. That becomes 110. But in order to do that, I'm going to separate the numerators, right? 110 s squared plus 9 plus 110, 1 all over s squared plus 9. Excellent. This guy right here,
Number 8.
so let's call this P of S. Let's call this guy H. S. Just because we're going to have a lot of them. So number 8, dead on. This is number 7, but what do we have to do? It's not quite number 7.
We gotta put an A up top, so we gotta add 0 thing. Is that
Not at 0, the other one.
add 1?
Yeah, not add 1.
Multiply by 1.
Multiply by 1. And okay, so what is the 1 in this case?
S squared plus 9? Over
3.
9? Okay.
What about 3?
3 over 3.
3 over 3. Just making sure it's 1, right? It's 3 over 3. Just want to keep emphasizing simple rules of algebra, and even that's like arithmetic, right? But that's why I think it's so fundamental. Adding 0, multiplying by 1. Do you realize how high in math we are to do that stuff, right? I love this circular. We're back.
See, and that's what I don't like about it.
It's beautiful.
There's like no point to it all.
No, you're missing the point now. I was like, it's that we're doing high level math with simple stuff. We go too far and everyone's, this new breakthrough. This is fundamentals. The things that they solved with the fundamentals that we need to understand. Oh, it's like, that should give you like a warm feeling inside. Okay, all right, so while we're at it, let's get this all the way out. Do inverse Laplace transform of G of S. So we got other mess to mess with, which I'm going to call G of T, which is, 110. All right, that was number 8, which makes that cosine of 3t plus that goes over, that goes down. This becomes then 1/30th sine of 3t. Okay, so we got that piece, all right, all the way out. Now let's grab h of s. I think that one needs a little bit more work. Okay, so for this guy, similar to what we did above, what do you think we should do?
Separated.
Yeah, let's pull these apart. it's just too hard to identify what I'm looking at when they're together. Now, sometimes you pull it apart and then put it back together. All right, so once I have that pulled apart, now what am I looking at? Does anything look familiar?
Is it the kind of same thing we just did?
It could be some of the 7 and 8, but
No, I mean, I agree. Could be 7 and 8. Could be basically anything 7 to, yeah, like 22. In order to identify what do they all have in common that this one doesn't at the moment?
they're factor.
Yeah.
Complete the square.
Complete the square. Again, simple concept. So b equals -6. B over 2 is -6 all over 2, which is -3, which makes c -3 squared, which is 9. And again, this is adding 0. So I'm going to add 9 and subtract 9. This piece right here then becomes s minus 3 quantity squared. And at the end here, 11 minus 6. I have that. Since, all right, now this is the denominator, right? So this is the denominator piece. Does that one start to look more familiar to something?
Yeah.
Specifically? This is the denominator. Where did it go?
17 or 18? No. 19, 20.
1920, right? Looks like 1920. All right. And so while I'm at it, I'm going to do one more thing to just make the denominator fit that exactly. Because it's got to be this form, right? Something squared. So what squared makes 6?
Square root 6.
Root 6. Just so we have it completely, right? And again, so I don't need to write this 10 times. Now I'm going to call this something else. Let's call this W. That is now our denominator, W. Okay, so that's because now that's a whole thing. Okay, so now back to what we have. H of S equals W all over negative 11 tenths S. Okay, well, while I fix this, let's write W on this one. I'm not going to write it on the other one. Okay, so we identified it's 19 and 20, which means this one's feeling pretty close. While I'm at it, let's pull that negative 11 halves to the front. 11 tenths, not halves, sorry. Negative 11 tenths, that goes out front. Okay, what do I need, all right, on this one to make it either 19 or 20? And which one should I be focusing on at the moment?
19.
Should I be focusing on 19? Why is it not 19?
Because 19's just to be on top. It needs to be 20 because there's an S.
S. It's the S that's screwing us up. This one, I'm 100% focused on 19 over here because that's a number. It's the S's that are the pains for us, right? And I saw it, right? That's what I was saying. I saw it as soon as we created the partial fraction because I was like, BS plus C. Soon as you do that, right? Like, that's when you know that basically this is in your future. Okay, so I have the S. So what do I need to do with that S? I need to add
0.
0. And specifically, what is 0 in this case? Do you see where we are?
I'm not, the whole adding zero thing, dude, it's,
This is definitely number 20, all right? So let's
Yeah.
just specify. This is number 20, all right, with A equals, all right, and B equals.
3.
So A is 3. All right, what is B?
square root of 6.
Root 6. All right, that's exactly what I'm looking at here. But this needs to have, all right, to match that form, it needs S minus 3, exactly how it looks right here. This piece needs to go right here. So I need a -3. But in order to do that, I also have to add 3. Because by definition, right, that is plus 0. I'm getting it there, but also getting it out of the way. Since I don't want that thing in my way, I basically take that other one off. All right, let's do this one even slower. That becomes this guy. The fraction in front goes with it. And then while we're at it, let's put the fraction all the way in front of this guy. That's basically what we have right now. And I could write this out. Technically, I can put this one over here too. This is 3 minus 3, right? When I drag it over here, all I'm doing is moving this back and forth. This whole thing is actually the 0 that I added. It wasn't actually just up here. It's actually this. This is how complicated the 0 was that I had to add to my equation, right? I bring it over because now this perfectly matches number 20, right? This is exactly what 20 looks like. Then I got to bring this because all this constant, but this is the easy part because there's no S here. S is the one that is our biggest problem. But once we have that dealt with, now I bring that over and whatever fraction this becomes, -33 plus 5 halves, all right? Then I just have to deal with whatever is remaining there. So what is that actually become? -10. Right, just to make sure. It's -33 plus, that would actually be 10, no, 25. 25 tenths, yeah, that is -8 okay. Because it's really just this piece, right, and this piece. Those pieces together make the remaining coefficient. And the coefficient is the part that we're keeping track of the most, without a doubt. Then in order to make this guy, this is clearly number 19. With A equal, and what is A here?
Root 6. No, 3.
3. What was that? A is 3 and B is root 6.
You
Right.
multiply there, root 6 over root 6.
So, yes, yes, because right again, I'm just matching up the form. I look at number 19, and I need B on top, right? So I multiply by 1, and in this case, my 1 is root 6 over root 6. One last time. This is why I want to call it W. Because I keep this thing over and over again. But it's good to keep track. And again, our coefficient is our everything. That is really, we identified the form way early of what this was. But identifying what that coefficient is, that's actually the hard part. So actually, what's the coefficient now?
8/10. No, or 8/10 is root 6.
And I mean, I could reduce that to 4/5 too, but. I was like, we're just keeping track so much, it doesn't really matter, right? I was like, that guy, because that one comes over all the way out, that one actually ends up in the function. So all the way out, inverse Laplace transform of what we called h of s, which will become h of t, -11/10 e to the 3t cosine root 6t minus 8/10 root 6 e to the 3t sine root 6t. Putting it all together, we're calling y of t actually. Y of t is then beautiful. And once again, this should look kind of familiar as well. E cosine, what kind of solution was that with our characteristic? When did you end up with e cosine and e sine?
It's not imaginary.
You ended up with you have imaginary solutions to characteristic. Oh, look, and there's the coefficients. All right, they're not pretty, and they're a hassle to find as well. And oh, look, sine plus cosine. Remember our undetermined coefficients? There we go. Undetermined coefficients. When you have a sine, your particular guess should be a sine plus b cosine, right? That's exactly what we have. I was like, and it solved all those. Remember the. Yeah. I was like, so, all right. The particular solution, finding those coefficients, it took a bunch of time. You had to solve with a bunch of derivatives, all right? And then you had to go back in and solve with a bunch of derivatives to find the solution from the general to the particular. This is, or general to the actual. This is the actual solution, right? All the coefficients are solved, right? It's just a matter of following your algebra. I was like, it's whichever method you're stronger at. And I like this goes all the way to the solution. I mean, that's big. Either that or you have to be a good guesser with particulars. As I said, I was going to mention. Now, the definition of Laplace transforms was based on initial condition t equals 0. We know, we've seen, t is not always equal to 0, right? It's not always y of 0 equals something, all right? We have other options. Now, just be aware, this section isn't tested upon because the problems just get a little bit longer. There's a couple of home funds that I just want you to look at, all right? But already you see these get kind of long. I was like, and I want you to be aware that, of course, we can solve when the initial condition is not 0. It's just you have to start with an initial step. That initial step is you do a transformation. Do a transformation, all right? In this case, notice the initial condition is 3. Oh, so well then, let x equal t minus 3, all right? And oh, look, when I put that in, 3 minus 3, I set it back to 0. That also means that the function has to transform a little bit, all right? Because if x equals t minus 3, t equals x plus 3, I put that into my equations, and you'll see that the equations, all right? Oh, we get initial values, right? It was 0, 0, and 7. So we still have 0 and 7, but our equation, all right, adjusts ever so slightly as well. So notice what it was. All right. this is of t here, right? Oh, look, I have cosine t minus 3. Now that becomes cosine of x. I have derivative of y, I have derivative of u, 4y, 4u. Oh, that's all the same. And notice that this was for t, but when I put in x plus 3, all right, in for t, it becomes 4x plus 12. That's actually it. Now, this is exactly an equation to solve. Solve it all down exactly like we were doing. Do Laplace transform, then do inverse Laplace transform, partial fraction fun. And at the end, okay, we've transformed it. Once again, we're in terms of x's. So it's a little bit at the beginning and a little bit at the end. So it just adds a little bit on both sides. I have x's here, but then remember, x actually equaled t minus 3. So it's kind of like doing our heavy sides at the end. Remember, we got the functions. And then, got to put in the t minus 3s. Same exact thing. Oh, look, wherever I had an x, I replace it with t minus 3. So it's almost exactly that same approach with the heavy sides. And that's why, right, it works so well. It's based on 0, but that's just a little bit at the beginning and a little bit at the end. It's just that much more you have to do. But again, still solving, all right, equations with algebra. To that end, let's investigate, like I said, all right, again, I spoiled it halfway through. I was like, the real strength of Laplace transforms is the Heaviside function, and that is because we determined the Heaviside function to be the transformation E. We did it because, all right, in the transformation and the actual definition of Laplace transforms, the transformation uses E, right? Because it is the natural number, right? It's the natural function, takes the derivative and integrals so smoothly. It's because there is no other transformation, all right, that handles on-off switches, stepwise functions, as well as Laplace transforms, all right? If you see it, now notice, all right, the directions, notice that we had on our last question, right? It said solve using Laplace transforms. So if it doesn't say that, you can pick your method. Notice what this one does not say. This says solve the IDP. Does it say use Laplace transforms? You have to know, I can only solve this with Laplace transforms. If you see a Heaviside function, there's no option. You have to use a Laplace transform. All right, so let's take a look. Transform the whole thing. All right, and I have the Heaviside function, and actually while I'm here, let's adjust this. Remember, when you have a Heaviside, the function associated needs to be in what form? Is it fine? It's just 4e to the 4 minus 2t? No, it is not. Just like we just talked about, everything needs to be in, right, whatever the Heaviside function is, like t minus 3, t minus 9. So in this case, it needs to be in the form t minus
2.
2. Why'd you pick 2?
You 2.
Because it literally has to match this. So I need this. Hopefully, I can either create this or it's already kind of in that form. What should I factor out of this to give me t minus 2? Negative 2. Yep. And that is exactly. All right, just to line up our formats. So good. Now remember, we saw before, this is once again, get to add 0 or multiply by 1, stuff like that. All right. But in this case, this one is already in the proper. All right. So once again, with linearity, break this whole thing apart. All right, and then recall the Laplace transform of the heavy side is the E function, e to the negative CS, and whatever the adjustment is. So in this case, negative 2s, and my function here, remember that we try and identify the actual function. Let's make a note here. F of t minus 2 is this guy, negative 2 to t minus 2, which means f of t is e to the negative 2t, and that's just number 3. Number 3 with negative 2, which means that becomes s plus 2. You okay, Josh?
Yeah.
Well, this one is, notice that the heavy side transforms to E, all right, and the E transforms to the fraction. So this is the transformation. We always identify, because technically we're using number 2, but also number, what's the adjustment function? 27. So number 27, all right, is where a heavy side is connected to another function, right? And so that's what makes this one interesting. But remember, look at the form of 27, right? F of t minus c. So you identify what the function is, all right? And then turn it into its normal function, and then you're just looking for that transformation. This is, remember, at the end, we put all those t minus 2's back in. But in the transform, can you tell that this is adjusted by t minus 2? Down here?
So
No, that's the whole point. You only know at the beginning and the end, and that's why that's the strength of Laplace transforms. You identify what the function actually is. It's actually where a equals negative 2. All right, you identify what the function is, and this is like the last step, or AKA the first step. The first thing you do is get rid of that t minus 2, all right, and we'll put it back at the end, because it has no bearing on actually solving this function. It is important to what the function actually is. All right, plug in our initial conditions. Simplify it down and separates stuff out. All right, divide that guy over. This one, we are going to keep separated because this is a normal function. This is a heavy side function. We need to make sure we separate because remember at the end, this one, when it goes back, it just goes back to t's. This will go back to t minus 2's. So we do have to keep them separate, right? Sometimes it might be easier, right? We saw that, remember we were combining multiple heavy sides and things like that. If they're all heavy sides, then you solve the function. But in this case, I was like, this one, I want to keep separated into heavy sides and non-heavy sides. Simplify this down, all right, at least because we've got 4 over s here. So we have two partial fractions to deal with. All right, call this guy g of s, call this guy h of s. And the whole thing is that again, when solving partial fractions, the fact that this is a heavy side is irrelevant. So I have e to the negative 2s times this function h of s. Once again, don't see a ton of good news. Does this thing factor? All right, s squared minus s plus 5. I was like, which means in both of these cases, cover up? Nope. All right. That is common. All right. That's why do not miss the opportunity to do cover up when you can. When I see people that are like, I just do it the long way every time. Why? I was like, when you have plenty of these. So make sure always factor it out whenever you can. Right. And again, partial fractions doesn't work unless the entire denominator is completely factored. Okay. You can't leave s squared minus 9 together and just do it the long way. You have to break that into s plus 3, s minus 3. Okay, so let's start with g of s. All right. Always want to practice, make sure we're good making a partial fraction. So let's make it. What does this become?
A over s. Plus, I guess, bs plus c.
All right. And we've got lots of fun other work to do. Plus, we're running out of time. So a equals 4. From there, it's all detail work. Faith, we could do that. Again, make sure at least we practice. What does this partial fraction become?
A over S plus two, then BS plus C over that.
All right, so the partial fractions again, skipping the heavy lift here. Because in both of these cases, I was like, when we end up with where we are, we have to do this, the heavy part is still yet to come. Both the cases, what do I need to fix in the denominators? Square. Let's complete the square real quick. I'll call it. Because both of them, right? I have the same denominator and I can see it. In both cases, I have S's in the numerator. B equals -1. -1/2 C equals B over 2 squared. I got 1/4, which means plus 1/4 minus 1/4. This becomes S.
What? Minus 1/2.
How'd you know that?
Yeah,
1/2 times 1/2 is
1/4.
1/4, then 1/2 plus 1/2 is 1.
Lots of ways. The other way, this is why we do this. It's always the B over 2 term, right? So I was like, you guys are both correct, 100%. But this one is no thinking. I write this out because it's literally this. I don't have to know what it is. I was like, I don't have to try and figure out like this, that. You guys are both correct. But when the numbers are √7 over √19, it's a lot tougher. And so I was just, hey,
Okay.
that guy. And then let's see, plus 19 force. One last step, because already, what do these guys look like? In the Laplace table, what's that look like?
Same as last time, 19.
Yeah, 19 and 20. So let's do one more little thing just to prepare. Looks like number 19 and 20, which means √19 all over 2 squared. All right, we will pick it up there next week.